So I'm delighted to open this session, which is organized by FFplus team. So we will talk today about the impact specifically. We are here essentially to showcase the real-world success of FFplus innovation studies, sub-projects issued from the first call. So just one word about FFplus. So FFplus is the successor of the Fortissimo series of programs. It's a European initiative dedicated to boosting the competitiveness of SMEs and startups by accelerating their adoption of high-performance computing and artificial intelligence methods. So this project provides access to supercomputing resources, empowering businesses to solve complex challenges through advanced modeling, data analytics, and generative AI innovation. So over the next 2 hours, we will explore how high-performance computing and AI are being harnessed to solve complex challenges across incredibly diverse fields. We have a lineup of speakers who are moving in their needles in their respective industries. So we will conclude at the end by a brief wrap-up. So our goal today is to show how FFplus supports the journey from ambitious idea to tangible innovation. So let's dive now to our first presentation made by Victoria Suarez from Facegen, which she will discuss generative craniofacial reconstruction of human identification. So Victoria is a partner and senior researcher at Panacea Cooperative Research in Spain. She's expert in bioinformatics and AI for forensic applications. She has more than 15 years of experience in research and development, and is also involved in the development of business strategies of Panacea. She has acted also as manager of the project Facegen, supporting the technical team composed by members of Panacea, main commercial partners with University of Granada and Envia in France. Please, Victoria, you can share your slides now.
Can you see it properly?
Yes, yes.
Okay, thank you very much. Well, thank you, Samir, for the introduction, and also to the FFplus Consortium for the opportunity to be here today and introduce to you our project Facegen. My name is Victoria, as Samir said, and I will tell you a little bit first about what Panacea is. Panacea is the only cooperative specialized in artificial intelligence in the world that we know of, and we work for developing products and also offering services with a great social impact. This is why we are focused on the forensic field, and our team together that is distributed in different regions of Spain, as you can see on the map. We put together more than 20 years of experience in the application of AI to forensics. So, like I said, making a positive impact on society is our main driver. And for this, we do a lot of research and development that the field requires. In this sense, we try to upgrade the TRL of different technologies that could be useful in the forensic field. And this can lead sometimes to products like a skeleton ID, which is the only comprehensive software that exists in the market for forensic identification using physical anthropology techniques. And we also offer services as a consultancy firm for the diverse problems that have to do with the application of AI, and this could go beyond forensics sometimes, including biomedicine and such. Of course, in the project Facegen, we were not alone. Like Samir mentioned, we made a consortium together with two big institutions. So being us, Panacea, the main commercial partner and leader of the project, we got critical support for specific aspects of the project from University of Granada, which is a long-term collaborator of ours that are particularly expert in trustworthiness of AI, which was a very relevant aspect of our project. And we also started a new collaboration with INRIA in France, given their high-level expertise in generative AI, which we greatly benefited from. So the context for our project and the problem that we want to tackle is the human identification problem. Nowadays, you can find millions of human remains still unidentified throughout the world. This can be related to historical memory or policial work, violent conflicts, environmental disasters, and so on. And for many of these cases, the solutions are not clear. Very often, we don't have any leads to start with the identification process. If there's no antemortem data, for example, that you can relate to, say, dental records, medical records, or a clear relationship with a demand from a person that's looking for a missing relative that you can go and apply DNA matching, for example. Many of those cases just tend to go cold because there's no way how to get started with the identification problem or the identification process. So our clients, our customers that are forensic experts mainly, they have communicated over and over again that they do need a solution for how to tackle these situations. And they, what they would like is to have a software solution for a specific technique that is specifically suited for the situation, that is craniofacial reconstruction. This is a forensic technique that can recreate the facial appearance of a person when everything that you have is the skeleton. Say that you have a skull in good condition. So from the model of the skull, a forensic artist would literally sculpt either with clay or assisted with non-specific 3D modeling software the soft tissue layers on top of this skull model to approximate the facial appearance of this person with the aim of then broadcasting this reconstruction. So maybe somebody can recognize this person and provide the initial clues to kickstart the identification process. So what is the problem? Well, this is, as you can imagine, a manual technique that is very labor intensive and slow, time consuming and costly for our users. So they were looking for an automated tool that they could use to essentially expedite what they do. And for these, there's some specific requirements that are involved in these high-stake fields of forensics, that besides demonstrating a morphological fidelity between the skull and the facial appearance, it's also trustworthy because they need to actually justify what they do with these models. So these are both main aspects of the Facegen project. So from Panacea, seeing this need, identifying this need in the market, we start thinking and we consider that the recent advances in generative AI offer a great opportunity for this particular problem. And by doing so, from a business perspective, we are hoping to create new revenue and consolidate our customer base, but also to expand and reinforce our network, either with our project partners, but also with collaborators and ultimately provide a relevant societal impact by providing this tool, making craniofacial reconstruction accessible, which nowadays is currently very limited to the expertise of just a few experts around the world. Now, with these ideas on the table, FFplus offers the perfect opportunity for us to develop and actually explore and move this forward. The Innovation Studies Call gives us the window to actually put to practice some of the technical ideas that we had, particularly through the support of an HPC access, in our case, particularly the Barcelona Supercomputing Center, that would actually make it feasible within a reasonable time frame. Otherwise, unfeasible for us with our resources of our own. So we design a work plan. And this work plan is intended to identify the best technical approach among different ideas that we had for this task of, well, using generative AI for CFR. This includes different types of generative AI models. And we consider particularly foundation diffusion models that are generative image-based models, and also training for specific purpose adversarial networks, starting from 3D image data, like medical data, that is highly dimensional, and the combination of all of these is what makes us need high computational requirements. In order to meet the forensic standards, as I mentioned already, special efforts have been made to increase the trustworthiness of the models, which has been another leg of the project. Particularly, these are the three approaches that we wanted to compare. Was one using adversarial networks, training on volumetric 3D images as such, which is what we have. We start with sets of CT scans that are 3D, and we could use them straight up for training. We segment the skull on one hand, and we segment the soft tissue on the other hand, and then we can train to learn the relationship between one and another. The second approach would be using the same type of model, adversarial networks, but instead of using the 3D images, we would use a simpler representation. We call it 2.5 dimension images. These are depth maps that are actually flat images that represent the depth, like the third dimension in the image, as a shade of gray. You can see an example here on the right hand. And lastly, we want to explore the potential of foundation diffusion models, which we know are great at generating faces, but their fidelity is still to be tested. So with all of these together, we have these generative AI models, different types of inputs, and we start our experiments. For these experiments, beforehand, we did some theoretical estimations of the computational requirements we were going to need. And so we estimated the amount of memory that we needed per unit of data, in this case, per unit of image, and calculated how many different experiments we were going to run and what would be more or less the expected consumption per experiment. And we combined all of this together, and the results were that we would need several years, longer than 4 years, to run if we were to use the one GPU that we can access at the time. Well, at the time, we still had, nothing has changed, still the GPU that we can access. Luckily, the access for Mare Nostrum 5, the accelerated partition, made it possible to develop the whole project as planned within the expected time of 10 months, which is a huge improvement. And these figures show more or less what the final results in terms of consumptions were. We ended up using around 20,000 GPU hours, but also around 20,000 CPU hours for image processing, and a large amount of disk storage space. So in the end, among the three approaches that we tested, we found the best results were obtained with the combination of using an adversarial network with the depth maps, but also normal maps. Here you have both on the right hand as input. And this strategy was based on a publication that we had identified in the proposal that you can follow up through that scientific reference down there. So with this, we actually worked with different sources for data, also a very relevant aspect in the project for us, because, well, it is sensitive data, so there was a lot of efforts devoted to, getting everything ready with internal review boards and ethics committees and everything being done according to the data management plan. And once we started working, actually, we found that even though we had access to several tens of thousands of images, particularly from the public repository NMD, we had to discard most of it because of lack of quality. Not so much because of the quality of the image itself, but because this being a database of CT scans from deceased people, the state of the person. So some of the cases were just not usable because of the presence of too many artifacts that we could not fix manually, or because of a well advanced, degraded state. But in any case, we put together a decent data set to work with, especially from deceased individuals through CT scans that we used to pre-train the generative model. And importantly, we also had access to CT scans of living donors, living data donors. That was a smaller data set, but it was, instead of being a CT that is taken like laying down, which also affects a little bit the appearance of the face, this was CT scan, CBCT, cone beam CT scans of living individuals, meaning that you could see the face standing up and without those issues of artifacts of degeneration of the tissue that we had in pre-training. So this fine-tuning in the end was really nice to see the final results representing good looking people. That is what it gives you the most recognizability for the purpose of craniofacial reconstruction. And what I can show you here is just one case example that we asked permission to show from our results. You can see on the left hand of the image the skull that we start with, what we segmented from the CT scan, and the face in the middle is the actual appearance of that subject. So that is the face that corresponds to the skull on the left. And through the approximation of using adversarial networks and the depth maps and normal maps as input, we generated the mesh that you can see on the right, which is quite close. We're really happy about these results. However, for objectifying the results, we did come up with some metrics, of course, which is critical in this kind of research. And the obvious idea would be to calculate what is the distance of the generated mesh to the real mesh, like do they align perfectly or not? And we found a mean, an average distance of 3.8 millimeters, but this is kind of difficult to interpret. So we were more reliant on the second type of metric that we came up with, which was making a ranking that was produced by a facial recognition software that would compare the generated mesh with real meshes and try to pair them correctly. So we would be looking among the whole database which face would resemble the most the face that we generated, and with that we built a ranking, and we found that we have percentile 90 of the ranking in 65% of cases, which is a very good result. Also, in terms of trustworthiness, we applied some of the techniques that are available out there, like attention maps, for example, and from those we were able to learn what were the regions in the skull that were the most informative for our model to work with. And also we were able to highlight some of the regions where the method struggles the most. But these techniques that were available, well, they had to be adapted because they're not particularly suited for this type of application. So there's still work, ongoing work in terms of, well, attention maps applied to generative AI, and we are very proud to be participating in this. And also, we were very interested in considering what is a non-inherent characteristic of the facial appearance, like, for example, changes in the weight of a person or changes in the age of the person will change the facial appearance. And we were able to actually tune these parameters in the model so we could provide this information as metadata, and the model would actually respond with coherent generation of the facial appearance with those specifications that we can include in the process. So all in all, we are quite happy with the results of the project. There's still more work to do. As you have seen in the examples, we focused on the generation of the morphology of the face, but to have a final visual product that is suitable for CFR, we still have to think about the texture. We have to actually provide color and be able to place hair and all of those. No? But we definitely can say that we were able to find the best approach for CFR using generative AI, and this includes the use of these metadata, like the body mass index and the age. We are very happy to have been able to work together with the University of Granada and with INRIA, particularly with INRIA. We were able to learn so much that we now have incorporated generative AI to our portfolio. And regarding trustworthiness, we have tested, well, methods that were already there, and we are able to develop our own. So that was a major breakthrough. And all in all, for the interest of our users, the most important achievement would be reducing the processing time in craniofacial reconstruction from what could take beyond a week to mere seconds, and being able to generate the facial morphology like that, which constitutes a radically transformative innovation that was well awaited. So at the same time, and with support of the FFplus monitoring team, we were developing the business plan for the future CFR tool that will come out of this. And this includes particularly 3 different revenue streams. One of them is the simplest one, that would be to create an add-on and integrate it into our current product, Skeleton AD. Like I mentioned before, it's a suite of forensic AI tools for human identification, and our users of Skeleton ID were already demanding this contribution, this new expansion to include CFR. But also, and most importantly, because our goal was to make craniofacial reconstruction accessible worldwide, for this software as a service version will be critical. So in this way, anyone, well, any forensic expert in the world can access this CFR generation tool through a website and retrieve the generated facial model to keep working with. So this unlocks full scalability, particularly supported with HPC access. The third source of revenue for us is to provide support and training, because this is such a change in the way of doing things that, of course, it's going to require, well, some training to do and make forensic experts acquainted with the use of AI tools that our forensic team is particularly good at. So at the moment, after finalizing the development of the project itself, we are in a validation phase. So for this, we have established a partnership between our co-op and two forensic experts specialized in CFR, widely recognized experts that are going to be able to test the tool, compare its results with their own, and guide us in further product development phases to ensure acceptability. Also, because the scientific basis of all these technologies in the forensic field is a critical aspect, we are engaged in a project with academic partners. First lined up is Charles University from Czech Republic, that is going to work to validate the reliability of our methods. So they will make their test with different data sets and assess the performance of the model. And of course, we hope to include more institutions in the future for this. And interestingly, because so far I have only spoken about the application of craniofacial reconstruction for the human identification problem, like a societal problem that needs to be addressed, there's also this other venue that CFR2 can be applied that where we have less experience with, honestly. And this would be using craniofacial reconstruction for museistic purposes. So this brings us to a different type of market segment where the craniofacial reconstruction is trying to, well, bring to life historical figures. For example, you can see some examples here that have been recreated with conventional methods, computer assisted in this case. So we can learn more about our past, and this combines, well, again, the presence of a skull, but also some historical records that can guide, especially the last stage of the craniofacial reconstruction, which is adding the color and texture to the model. So yeah, any if you guys know of people interested in this type of application, we are happy to hear about it, since this is not our usual customer base. So in general, with the project, we can say that this is the only automated tool, is going to be the only automated tool in the market, and it's of European development. We're very proud of this. Also, thank you to the SaaS model, business model, and the HPC support. We are making craniofacial reconstruction accessible worldwide and in just mere seconds, which is great. And most importantly, this tool may mean a last chance for thousands of cases that keep accumulating, since all these sources of forgotten human remains are not stopping. In fact, they're expected to increase in the future. Violent conflicts and environmental disasters in a climate change context. We hope that this will make a real impact in society in general. So I think you can, contact us and know more about what we do through our social media and particular website and YouTube channel and so on. And I am also including my own email here in case you have any questions, but I will be happy to take any from you at the moment. Thank you very much.
Thank you very much, Victoria, for this interesting work and this interesting presentation.
So first of all, let me introduce my company, that is Webratio, or Webratio, as we like to say with our Latin pronunciation, is a company established in 2001 in Italy, as you probably understand from the strong accent. the main focus of the company since the first day was to find a way to let developers create software, initially web applications, without writing a line of code. So the background idea is that a traditional modeling technique can be used to describe visually, with a visual model, which are the behaviors of an application, and that an automatic generation system can produce the code of the running application instead of the human. And this is what we did from the first day, and what we are still doing, improving our platform, whose name is Webratio platform, as the company, with the same name of the company. To do that, we invented a modeling language whose name is Interaction Flow Modeling Language, IFML. This is exactly a visual model that we use to represent the way that the application behaves. So the way the application, the front end of the application interacts with the user, and the way that the business logic is executed. Webratio was initially a spin-off of Politecnico of Milan, but today is a privately owned company, owned by the RES group, that was also partner of the project, of the ALGO project. In particular, RES group was the expert in AI and ASPC subject. This picture just to give you an idea of what a low-code platform is. This is an animated screen of a Webratio platform, where you can see a visual representation of a web application. The bigger white boxes are pages, the smaller green boxes are contents, the small round circles with arrows going outside from them are hyperlinks, and so on. So this is a real application that we described using our visual model. In a traditional way for us, meaning using point and click. So there is a developer, they use point and click here, use menu to design the application visually. So that was our starting point. And what kind of business problem we are trying to address with our ALGO project? Well, not today, it's 5, 10 years that we are in this situation where digital transformation is continuously accelerating, and there is a growing demand from companies to being able to transform their business in a digital manner, and to keep the pace of the requirements of the users, because consumers are used to use consumer application that have a certain level of complexity and a certain level of usability, and they expect this kind of complexity and usability even in business applications, and this is generating a growing backlog to application leaders that are not able to solve and to bring to zero. And this is also due to lack of skills and or lack of skilled resources or skilled developers that they can actually implement those growing backlogs. And this is the context in which we play. And in this landscape, for sure, we feel a competitive pressure that is growing, because generative AI is somehow reshaping the software development practice. Maybe some of you heard about the vibe coding approach, and this is pushing local platforms to innovate their approach to development, somehow to avoid churn. And in this context, we saw a potential opportunity to accelerate the low-code adoption by complementing our visual point-and-click development approach with kind of declarative development through prompts. And also we have seen, thanks to some interviews to worldwide analysts, that actually the leading local platforms, our competitors, have an agenda that is filled with AI-driven prototyping features they are planning to do, or they actually already ran out, published. So the idea of the innovation is to infuse the low-code software development platform with generative AI to allow what we call the vibe low coding, so prompt-based low-code generation instead of prompt-based code generation. Our aim, so the aim of this innovation, is to further accelerate the development speed up to 50% of the professional developers, but also to we aim also to expand the adoption of the platform that today is mainly focused to professional, is mainly targeted to professional developers, but we want to address it also to citizen developers that are less expert users, less IT expert users, because the copilot approach can dramatically reduce the barriers to the adoption of the platform. And we also have this idea of differentiate our platform from the competitors, because we want to offer a step-by-step AI assistant that enables fully customized development of applications. That's our competitors by now are not able to do, because they started from a kind of template generation using generative AI, so generation of stubs of well-known business case that can then be extended using the traditional point-and-click approach. Which is our target market? Well, we are currently targeting, and we believe we will continue to do that, mid and large size EU companies. Since we are selling them a development platform, these companies, of course, should have an internal IT department that wants to keep the ownership of the development of their applications, or at least keep the ownership of the core digitalized processes. Inside those kind of companies, the target audience is made of IT leaders and head of business functions. The IT leaders are those managers that feel the pain of the pressure of the digital transformation and the pressure of the growing backlog they are not able to reduce. And on the other hand, the head of business function are those managers that have the requirement of digitalizing their business. Inside this audience, the main users of our platform, that are the main users we are targeting, are professional local developers, and with the innovation, we include also citizen developers. So those users that aim to accelerate their development speed and also aim to be involved in the software development life cycle without being IT experts. Which is the approach we investigated during the innovation project. Well, the idea was to fine-tune a large language model to let him understand our domain-specific language, so the interaction flow modeling language, the modeling language we use to describe applications. So to let the large language model be able to generate those IFML models for us. Well, IFML describes only the visual representation of the model, and then we decided to store those models in XML. So actually, the XML code is the code the large language model has to learn. we did this fine-tuning using our very large code base of IFML models we created in the last 10 years, more or less, using our platform. More than 10 years, but we filtered them out in the last 10 years. And we created a training set that is made of pairs of prompts and code samples. These code samples, of course, are extracted by our code base of models, while the prompts have been generated using foundation LLMs that we trained, or actually we prompted to train them to be able to produce prompts like a regular platform user would write to create that code, or prompts like a non-platform expert or a non-IT expert would write to get that piece of code from the platform. Everything has been done with the support of HPC resources, of course, both the fine-tuning, but initially also the generation of the prompts. So we used the Leonardo from Cineca, HPC resources. The idea was to find the smallest possible model to fine-tune to allow a broad adoption of the technology, because we can offer, of course, the generation capabilities from our cloud services, but we also have target customers that want to keep the generative environment on their premises, so they need to be able to host it. And of course, it's also a matter of cost of offering these services on the cloud. And to do that, we use to do the training of our system, and also to create the training set, to generate the training set. We used more or less 120,000 GPU hours. That is more or less 1 million CPU hours of Leonardo Cineca during the 10 months duration of the project. We experimented different foundation large language model like DeepSeek for training set generation, GPT also for training set generation, Mistral, and one from Meta for the fine-tuning and the ability of generating IFML code. Then the result we achieved, that is a trained large language model, has been integrated, or at least preliminarily integrated inside our platform in a pre-alpha version of the platform. And this picture tries to explain how we did. I mean, on the left, in the big green box, you see the design time. Design time is the moment in which a developer creates the application. So on the bottom with the Webratio logo, you see the traditional point-and-click approach that somehow integrates with the new Copilot approach based on the large language model we trained. Both the environments collaborate to create IFML models. Those IFML models are transferred at build time. Build time is a stage where the actual executable code is generated, starting from the IFML model. And then at the very end, on the right, in the purple box, you see the runtime, where the actual generated code in traditional programming code technologies is executed. At present, Webratio platform supports an output technology based on Java, Spring, Angular for the front end, and so on, and Cordova for mobile application. And this is the final result integrated into Webratio platform. I have a short video here. Let me see if I can play it. No. Yes, it plays. So this is the new way of collaborating inside Webratio platform with a mixture of point and click and interaction with the Copilot based on our generative AI technology. And here a developer is asking to the Copilot to add to this existing project of an application to add a product page that displays a list of products showing each product's name and price. The list should be sorted alphabetically by name in ascending order, and the platform is asking to the large language model to generate a piece of model that is able to implement this requirement, this description, and the large language model is actually producing it, including it into the new page into the existing model. After that, Webratio platform is able to automatically generate the code of the running application and start the execution of the page, as you can see it now. So everything that we did and the results that we achieved allows us to, first of all, keep the pace of the competitors. So compete on the low-code market landscape that is getting crowded every day. To compete in this segment, of course, we are trying to increase, and we actually achieved it, the development speed that we offer to professional developers. And we measured with the preliminary results of this development, of this innovation, we measured an average 50% increase in development speed in between, comparing the traditional point-and-click approach with the prompt-based approach. Consider that our low-code platform offers, with the traditional point-and-click approach, offers a 700% increase of development speed if compared with a traditional programming development approach. Then, of course, one of the impacts we are measuring and we want to measure and to achieve is the mitigation of the risk of churn of our existing customers that, of course, are looking also to the market crowded by competitors and are every day pushed by competitors in adopting their competing technology. And also allow us to modify our business model and to extend our market to these potential new users that are the citizen developers. So, as I told you before, developers that don't have expertise in IT. Given this, and given the results that we have been able to validate, so to validate the vision that we have at the beginning of the project, and also to validate the technical approach that we were foreseeing, we are now able to plan next steps that include a go-to-market that we started of this initial innovation. That means move from the pre-alpha prototype version of ALGO to an alpha version we want to make available to early adopters. And we are working now on this. Secondly, to expand the large language model capabilities to encompass also the generation of data models and not only user interactions. but also business process models and business logic execution. And we applied to the second call of Fortissimo to finance this investment. And we are also looking forward to the ability of work in a multi-page generation way. Today, the ALGO project focuses on a single page generation that allows us to ingest user stories and epics and produce end-to-end functioning applications, including multi-screen, APIs, data models, and so on. And that's it. So if you're interested in our activities, please stay connected. You can contact me on LinkedIn, just scanning my QR code, or write an email at the address you can see on the page.
So the goal of the FFplus project was combining high-performance computing and AI to deliver a scalable and explainable solution for asset managers. As a company, what we do is using and leveraging artificial intelligence, and especially machine learning and deep learning within the artificial intelligence space, to provide our customers with predictive AI solutions that are aimed at improving the performance of their investment strategies in financial markets, and more specifically to the equity market. In our vision, the investment management market has been completely reshaped by the use of AI, especially with regard to quantitative strategies. Most of the markets have the characteristics of having very low signal to noise ratio. So it's extremely hard to identify correlations between input variable to deliver overperformance with respect to the benchmark. As a company, we started using AI very early. We started our venture in 2026, being part of the acceleration program run by ING Bank in the Netherlands. And then following this participation, ING made the first investment into our company. And then in the following rounds that we closed them together with ING, UniCredit and Cassa Depositi e Prestiti, which is the Italian venture capital arm of the Ministry of Economic Development, joined ING as a shareholder in our company. We also got funding from venture capitals, both in Italy and in the US. Our main partners are research institutions, universities, and data providers, and high-performance computing providers such as Cineca. More specifically, the challenge that the market currently addresses is the fact that there is an increasing amount of data available in the financial market space, and the traditional statistical methods are not fully exploiting the value that it's possible to extract from data to predict stock behavior. Artificial intelligence, and especially machine learning and deep learning, on the other hand, have this possibility. These technologies are extremely powerful. Of course, they're prone to errors, like all traditional statistical methods. But in terms of predictive power that can be extracted, they are much more powerful in the success that can be achieved. As you can imagine, combining artificial intelligence, high-performance computing, such highly complex, very quickly evolving technologies in a sector which is also extremely sophisticated and crowded and challenging, such as financial markets, is extremely hard to do. And for this reason, it's necessary to have access to quality data, a lot of computing power, and being able to combine these two technologies together. In terms of the solutions that we currently provide to our customers, we have two main products, Axion Foresight and Axion Iris. Both these products are aimed at providing insights and suggestions to our customers with respect to thematic indexes with Axion Foresight, so we and our customers can quickly create thematic screenings and backtest generation with a human-in-the-loop framework to launch new financial products in the markets based on the selections of the stocks identified by our Foresight agentic AI software. And Axion Iris, which is a predictive AI-based software that predicts stock behavior and more specifically ranks stocks with respect to the probability that each stock will over and underperform the market. And then once you have a ranking, you can build model investment strategies on top of that to launch in partnership with regulated entities such as banks, asset managers, hedge funds, financial products. Now, before jumping into the details of what we did in the FFplus project, a few inputs and information on what our process looks like. So in terms of the pipeline that we follow at Axion for building AI models, we start from identifying the input data that can be used to predict stock behavior, data that comes from both traditional data providers and alternative data providers, such as fundamentals, technical data, macroeconomic data, context data, and less traditional data as analyst estimates, sentiment, news data that can provide color on how the market is evolving over time. Once we have identified this data and we have pre-processed this data to make sure that they are point in time, that there is no data leakage, and that we have divided the data set into training, validation, meta-validation, out of sample, and so on. We start with the modeling of the AI modeling. So starting from approximately 100,000 plus model architectures that we have available in our platform, we identify the best performing models, and then we provide an additional layer. Once we have identified the best performing models, what we do is ensembling them, trying to come up with approximately 50 models that we use live. And these 50 models selected among the more than 100,000 models that are initially available, these 50 models that we use live needs to be as decorrelated as possible between each other to ensure that the performance of the models and the strategies is consistent over time in different market scenarios and for each stock that we focus on. And then there is the building of the model strategy, the model investment strategy, that takes into account the customizations that our customers ask us to develop, such as long only versus long short strategies, more or less concentrated investment strategies, and compliance with the regulations that our customers need to comply with. As I said briefly before, our target customer audience is composed by all players operating in the financial markets space, more specifically asset managers, hedge funds, private banks. You can see here a few examples of our customers. Now, let's jump into the activity that we perform thanks to the FFplus program and see how the process was, also trying to highlight both the benefits that we were able to achieve and the challenges that we faced during this the last 10 months of the project. So in terms of the partners involved in the project, it was us as the end user and coordinator of the project, and the University of Modena, which is the research center that we have collaborated with since quite a lot of years ago, providing the research capabilities and skills that that was necessary to build to build the solution that we have developed thanks to the FFplus funding. Also in the project, we have leveraged the Cineca Leonardo infrastructure thanks to the European HPC JU computing power that was that we got access to. The ultimate goal of this project was to build a transparency explainability layer on top of our predictive AI. And more specifically, the goal for our customer was not only to have access to highly accurate predictions on which stock will under and overperform the market, but more specifically, the goal, one of the main challenges that our customers face is being able to explain why a certain stock was predicted to be better in terms of price or increased price with respect to the other stocks in the investable universes that we focus on. So both for compliance reasons and for communication and transparency towards their customers, they were asking us, why are your AI models selecting this stock and not another, this ETF and not another ETF? So as AI is a deterministic technology, so same input, always the same output, even if it is deterministic, it's not enough to explain why a certain stock or ETF was picked with respect to another one. So what we decided to develop was to build a software, well, a transparency layer on top of our predictions that was able to explain and generate reports in the same natural language format that our customers are used to receive from their providers. And so our approach, more specifically, was to develop a large language model with a financial domain expertise that could include the forecasts of our predictive AI models, the sharp attributions value that we were already creating, metadata, market context data, and more in general, all the other data that we already source, and build an LLM that was able to create reports in the same format that our customers were already using. And of course, HPC was crucial in this experiment because it would have been otherwise completely unfeasible and unrealistic to develop and fine-tune an LLM network. In terms of number of GPU hours, we used slightly less than 50,000 GPU hours on the Leonardo supercomputing infrastructure at Cineca. We have benchmarked approximately 15 commercial open-weight LLM using LLM as a judge methodology to assess which one was performing better, and created approximately 50,000 sample instruction-based dataset for the financial domain training. The main achievements that we were able to get thanks to the FFplus project were, well, first, a benchmarking framework. As I said before, we validated approximately 15 open-weight models, enabling an objective comparison in terms of the explainability task that they were aimed for, with a gain, a measurable improvement actually of plus than 50% compared to the base models. So confirming that the approach that we choose was effective. And then we have fine-tuned 3 models, the best performing ones, Llama, Gemma, and Quen, successfully fine-tuning this model for using a parameter efficient technique. And more specifically, Quen 2.5 was the best model architecture in terms of the outcome. As I said, the main achievement, the main outcome of this activity was being able to generate a report. So this is what I'm talking about. A report that explains why a certain strategy has not performed well or has performed very well, which sectors within the investable universe were performing better and for what reasons, which input data our models were more looking at with respect to the other input data that they have access to. This is very, let's say, product oriented, very technical. The main business impact that we were able to achieve, provided of course that this is not live yet and it's based on estimates, as we have already applied to the phase 2 of the FFplus project. So we are not using the outcome of the FFplus phase 1 project yet with customers, only doing internal testing and streamlining internal process. So in terms of the estimated business impact, there are 3 main benefits that we were able to achieve. First, expanding the target market by an approximately improvement of 10% in the serviceable obtainable market. And this is mostly due to the fact that a portion of our customers, even if they were interested in our predictive AI models, they could not use them because there was not this explainability layer on top of the predictive models. And thus, they were not able to provide explanations to the regulatory entities, central banks, and well, the third-party regulatory entities, and also they were not able to explain to their customers why a specific investment decision was undertaken. So thanks to this additional new transparency and interpretability feature, we are able now to serve this larger market, target market. Secondly, a revenue upside. So by providing this additional feature, we aim at increasing the average revenue per user of approximately 15%. And that results in approximately $500,000 in potential additional revenues at the current customer adoption rate. Third, less costs. So right now, to serve these customers without the interpretability feature, we spend approximately 1 full-time equivalent month per client per year, with a total cost of approximately $400K per year at 70 customers. So a combined benefit that, if we take into account both the additional revenues and the cost reduction, of approximately €1 million per year. And that is in addition to the extended available market that we are able to serve. As I said before, the benefits are significant, but we also faced challenges during the process. More specifically, some delay in the initial access to the supercomputing infrastructure, then early model hallucinations and instability. So that was probably, from the technical modeling point of view, the hardest challenge that we faced. It was the first time that we were using LLM models to, well, in general, and I mean, using large language models for explainability on top of predictive AI, that creates quite a complex and very easy for hallucinations scenario. So we had to change our approach in order to avoid these model hallucinations, and also due to the large amount of data available, a lot of out of memory issues during the fine tuning of the LLMs. In terms of the mitigation, that during the last 10 months we applied, well, the 10 months of the project we applied, well, local experimentation during the HPC initial delayed periods where that's what we did. And for the avoidance of model hallucination, we shifted from an autoregressive to an instruction-based fine-tuning approach with I mean, ultimately no significant impact in terms of the final objectives or scope of the project, and all the deliverables were achieved on schedule. So to summarize the challenges that we encountered during the 10-month project, well, the business benefits, and ultimately there was not significant impact, but as probably is very common in every R&D project, there have been some issues, some problems that fortunately we were able to solve, thanks also to the expertise and support of University of Modena and the personnel of Cineca, who helped us all along the 10-month period. In terms of the next steps and what we are, if we get approved for the phase 2, that's what we want to develop next. So the immediate next step would be a further validation of the accuracy and compliance readiness of the models, with an extended explainability features that we want to develop under the FFplus phase 2, if approved. And then at the conclusion of the FFplus phase 2 project, of course, commercial deployment of what we have developed, with the possibility of integrating the explainability as a priced product features, as I said before, continuing and extend, if possible, the collaboration with the research institutions that we partner with, Unimore and Cineca, and further research for model evaluation, quantization, and parameter efficient fine-tuning all along the process, and, well, possibly not only linked to the specific features that we have developed and will develop in the future. Now, more in general, if I think about the well, all the process and steps that we undertake since our inception, having access to high performance computing was a key ingredient for our business. When we started, we were approximately, well, we started, I was one of the 3 co-founders. And then after the first year, we were approximately 5 or 6 people in the company. Now we are about 50 people. So we have expanded our team significantly. And the possibility, the opportunity to participate in European projects, local projects that founded or co-founded the research and development activity was a key component to attract new investors, improve the product, of course, and having also a public recognition that what we do is at the edge of AI and high performance computing applied, in our case, to financial markets. Here you can see a brief overview of all the projects that we have been part of, starting in 2018 with SHAPE, and then ESAX, the NCC Italy experiment, FF4, and recently the FFplus project that I briefly presented before. All these projects, without entering too much into details, allowed us to build the infrastructure and then to improve it, combining high performance computing, AI, and specifically AI applied to financial markets, which is quite something that in the last couple of years we have been seeing quite a lot. A lot of peers, competitors have started doing this. One of the main advantages that we had was that we were able to start very early in this process. And as I said, combining the expertise of Cineca, research center, universities, has really proved to be a significant competitive advantage with respect to what other companies are doing. That's it. Very happy to answer questions if you have any.
Hi everyone, my name is Patrick Sabol from Geotetica Vision, and now I will present you the results of our project in FFplus, named Foundation Model for Geospatial Analysis. In this project, two partners were in this consortium. We, Geotetica Vision, as SME and application lead. In this project, we provided 15 plus years of geospatial expertise, and here we define business and requirements and use cases. And our consortium partners from Slovakia, Slovak Academy of Sciences, partially provided high performance computing infrastructure and is specialized in large scale distributed AI training. So let me introduce our philosophy of Geotetica Vision, which is that decision makers have to make better decisions, and better decisions require better understanding of reality, and we cannot have better understanding without better information based on better data. Therefore, in Geotetica Vision, which is a Košice-based geo AI company, we handle the full pipeline of this. First, we handle data collection through drones, or we process aerial and satellite data, which we are using to extract information using AI, deep learning, and computer vision technology. And so we turn pixels into classified layers. So we turn pixels into informations, and all these extracted information we deliver through WebGIS and digital twins solutions, where we provide also spatial data management and photorealistic rendering. But the main product from Geotetica Vision is Cartographer platform, which is software as a service platform designed to democratize high-end geospatial analysis, which converts raw satellite or aerial imagery into clean, usable map data. Important to say here is that we do not generate simple pixel segmentation masks, but directly vector polygons in just minutes. And this platform should allows non-technical users like city planners to perform complex mapping tasks without needing to be GIS experts. For Cartographer platform success, we are facing a critical business barrier, which is scalability. We call this as data hunger bottleneck, because traditional AI models do not generalize well, and which means that model trained only on Slovakia fails to perform well on other European regions. For example, we spent 170,000 euros on labeling our proprietary segmentation data, which lasts more than 6 months. And to adapt to new regions, we still need to spend such money and time to be ready for new regions. And this high cost and delay made global expansion economically impossible for us. So one solution was the foundation model. So we basically shift our solution from a paradigm, one model per task to one model for many tasks, which is represented by foundation model. Which means that instead of training from scratch every time for new task and region, we train one massive model once, which can be rapidly adapted or fine-tuned for a new domain. And this turns our AI into reusable assets, which also slashes our time to market from months to just weeks. So this is overview of solution architecture. So basically, foundation model which generate embedding for any type of geospatial imagery could be used to fine-tune new models for segmentation, classification, and those models will power cartographer to deliver segmentation and vectorization directly to the users. To build this, we required massive computing resources. So basically, first we need to acquire massive data set for foundation model. Then we need to train this foundation model architecture. And finally, we can fine-tune this model on downstream tasks, which allow us to validate this approach. So as a first step, we needed to acquire foundation model datasets. For this purpose, we aggregated open web map services imagery from 70 European countries. For this, we implemented custom Python scripts for high zoom imagery downloads. And to download this imagery, we employ HPC Devana in Slovakia, which we used for downloading and post-processing of these imageries or raw imageries into ready to train datasets for foundation model. And this this dataset was then transferred to Marenstrom 5 for training foundation model. Here is the simple estimation that without this HPC access, it will last 7 months to gather all these datasets. And using HPC, we have ready datasets in only 1 month. So for step 2, to train foundation model architecture was or is a vision transformer. This architecture was trained in self-supervised learning, which means that for this step we did not need any labels for the training. And this foundation model was trained in a masked autoencoder approach, which means that it's a simple idea that we masked more than 75% of the image, and the goal of the model was to reconstruct the final image. This way, well, the final reconstruct image is not useful for us or important for us. What is important is that this way the foundation model could learn the features, geographical features from Europe in a simple way. Regarding the model training, for this purpose, first we done some benchmark for scaling of the training foundation model. We found out that using 64 GPUs in parallel, we achieved almost 50 speed up, which is near linear scaling. And for optimized training and to prevent bias, we implement custom data loader where we made sure that to each batch sample from different land use like forest or urban area where or all samples were presented in this batch. That's the problem. We prevent the problem because basically raw European data are from around 80% forest or any kind of vegetation. Then we run some optimization strategy to train foundation model. First, we train tiny and small variants of the foundation model with less parameters. Here we performed hyperparameter optimization, and when we found the best optimization parameters, then we run training of the large model with more than 600 million parameters. Finally, we spent more than 700 GPU hours to train foundation models, including also the optimization of hyperparameters, which when we compare to single GPU work, this will take us more than 8 hours of 8 years to train such foundation model. And thanks to HPC access, we done this in more than 1 month. So finally, to validate this foundation model, as I said, we create precise segmentation land use datasets of 14 classes, which is mainly from Slovakia domain. And for training or fine-tuning foundation model, we exclusively used data from Slovakia region. And for testing, we validate this foundation model on other EU regions. So basically out of domain from a segmentation model. And also we run more than 180 parallel training runs to optimize other parameters of the foundation model and segmentation model. So the results were a breakthrough for us. As you can see, our foundation model improved accuracy by 18% on Slovakia regions, comparing to a model trained from scratch. And mainly, it generalized 2 times better globally compared to training from scratch. And what is most importantly, that we train model with only a part of the data sets with more than 12% of the data. And this model almost maintain the full performance of the model trained on full data sets. from these results, we have business impacts by reducing label needs by 87%. We also reduced labeling costs, which also reduced the time to label new regions or new tasks 6 times, and the final return of investments in this project is more than 140% realized with just 2 data sets. Also, because of access to HPC infrastructure, comparing to cloud providers, we could save or we saved more than 300,000 euros in a computing infrastructure. And our projected revenue for our cartographer platform through numbers of subscription and API access is more than 2.5 million euros projected for next 3 years. So basically, who benefits from this approach in Europe? First of all, it is our primary end user of our cartographer platform, which are the municipalities. Basically, we can now target more than 700 European cities where they can use our product in use cases such urban planning, zoning, or infrastructure management. And also other government agencies are our end users, which will be used for national mapping or any other environmental organizations. And we also plan to open source our foundation models and datasets. From this, also other European SMEs and startups can benefit by accessing our foundation models, and also research and academic community could benefit from this open access. As I said, the scalability across EU regions is the main result from this project, because in old way the SMEs will need to would need spend more than 6 months and thousands euros to gather some massive data sets, local data sets. By this approach, we can scale, or any other SMEs could scale their approach to across all EU regions. And mainly, they could spend less euros to label data, and they will provide their solution 6 times faster. From socioeconomic impacts, in this way, we democratize AI in this domain by making high-end analytics accessible for all those municipalities and end users. And mainly, we are strengthening EU sovereignty by delivering first open source European geospatial foundation model and datasets. So we help to reduce reliance on non-European providers of such services. And by 6 times faster fine-tuning, we can also enable rapid reaction to some catastrophic issues. And for next our work, we, as I said, we now are going to target more than 700 European municipalities, and we are going to open models, open sourced models and data sets. And we already submit proposal for second FFplus call, where we want to transform from a purely vision foundation model to vision language foundation model. And this model will understand the semantic prompts from the users, which unlock the zero-shot capabilities, which means that user will not need to use published models in a cartographer platform, but also can well easily say create their custom segmentation models by enabling them to get input using semantic prompts. So that's all from my side.